Right, so good morning again and welcome, guys. Hope you have been having a good week. And we have a wonderful class ahead of us where we're going to be getting into the process of electrolysis today. Just want to remind you that you should have 2 accounts in Canvas for each subject, for chemistry, for biology, right? You should have 1 account which gives you access to the recordings from last year. And then 1 account should be the current classes for this year, right? So just want to remind you why it is that you would see both of them in your account is because I'm aware that at different schools, because you're all coming from different schools, you will be doing the topics at different paces, right? So sometimes right now in some schools, you may be doing acid bases and salts, but I'm doing electrolysis here. So if it is that your school is doing a different topic than what I'm doing, you can use the recordings from last year to help to guide you, right? To help to guide you so that if you have a test coming up at school or something, then you can use the last year recording and then you can just make sure you're up to speed with what is happening in school. So that's why you had the recordings from last year. And of course, the ones for this year are in the course called Exam 2022. All right, so we are going to be getting on with the electrolysis that we started last week. All right, so we had looked at the principles of electrolysis. All right, so we are going to be continuing now. So I want you to go to your supplemental notes. We're going to go right where we stopped. And of course, I'm going to be giving you some additional notes as well. And we had learned about what electrolysis is. I wonder who can tell me, who can remind me of what electrolysis is. So who can give me a definition? What is electrolysis? I'm just going to the page where we had stopped while somebody is going to tell me what is electrolysis. Nobody's going to help? Anybody? What is it? Because we have to remember the basics before we continue. There is a real definition. Yesterday, last week, I gave you a definition. And I said, this is the definition of electrolysis. And I want somebody to look back at the notes and tell me a definition. We need a definition, guys. We can't be continuing and you don't remember what is the definition.
It is the chemical deposition of an aqueous or molten ionic compound by the passage of an electric
Go ahead
current.
again for me. Repeat.
Miss, it is the chemical deposition of an aqueous or molten ionic compound by the passage of an electric current.
Thank you. All right. So it is the decomposition of a molten or ionic compound by the passage of an electric current. All right. So remember we spoke about that and we said, all right, you have to make sure that you have an electric current present, right? And pass it through an electrolyte. Question, what is an electrolyte? Well, somebody, you just said it. So an electrolyte is a molten or, everybody needs to know this. An electrolyte is a molten or aqueous ionic compound, okay? Molten or aqueous ionic compound, all right? And when you pass the current into the aqueous or molten ionic compound, the electric current is going to cause it to decompose. All right. So we had spoken about that. Now remember now we spoke about how we set up the electrolysis cell. So the electrolysis cell is set up with an energy source, which is usually the battery, right? And we have two electrodes attached to the batteries. One electrode that is attached to the positive terminal of the battery is known as the anode. And because it is positive, it will attract to it negative ions, right? Because opposites attract. So if the electrode is positive, then we will have the oppositely charged ions. So the anions go to the anode, the cations go to the cathode. The cathode is negatively charged. Now, another thing I said to you last week is that electrolysis is a redox process. Who can remind me as to why I said it was a redox process? Why is it a redox process? Go ahead. So the answer here was that because we have oxidation and reduction taking place, that's why it is considered to be redox. Yes, so where does the oxidation take place, guys? At which electrode does the oxidation take place? The anode is where oxidation takes place. And remember that oxidation means that you are losing electrons. All right. So, or negative ions go to the anode to lose electrons. Why am I repeating this? Because we're going to actually be doing the electrolysis today. So you have to remember these things, right? Then the cathode is the negatively charged electrode, and our cations go there to gain electrons. All right. And then they will be changed. So remember, like electrolysis is like the reverse of bonding, where we are literally breaking a compound apart to get back the substances that it was made from, okay? Then we had gone through different electrolytes, strong electrolytes, weak electrolytes, looked at those which are non-electrolytes, and then we looked at electrodes. Electrodes are these metal plates that we put in the beaker. They conduct the electric current for us because they have mobile electrons, but they do not get decomposed by the current, okay? They don't get decomposed by the current. They allow the current to pass through them, but they don't get decomposed in the process. All right, with that being said, we are going to be continuing to look at the first process of electrolysis. We're going to actually see the first one being done, which is the electrolysis of a molten compound. But before I even go through that, I want to give you a guide as to what you do when you're doing electrolysis of molten compounds, right? So I'm going to ask you to write something for me. I love to give you guidelines so that when you're in your private study time, you can read it and remember exactly what to do. So we are going to be looking at the electrolysis of molten compounds, of molten electrolytes. So the electrolysis of molten electrolytes is our topic now. And for example, let me give an example. For example, what if you had, in this case, I'm just going to say sodium chloride liquid. So the key thing is that when you have an ionic compound that is molten, you're going to see that it is in the liquid state. All right. So molten ionic compounds have mobile ions in the liquid states and there is no water present. This means that it will have one cation that will go to the cathode to gain electrons to become atoms again. And I want to remind you that at the cathode we have reduction. Once you're gaining electrons, that's reduction. When a solid is formed, at the cathode, we say that it is deposited. There will be one anion that goes to the anode to lose electrons to become an element again. That is oxidation. When a liquid or gas is formed at the anode, we say it is liberated. So if a solid is being formed, we say the solid is being deposited. If it is a liquid or a gas, we say it is being liberated. Almost there. We must write the half equations. So we must write the half equations for each electrode. And then we combine them to form the full equation for the reaction. All right, so that is all I wanted to tell you, just to guide you as to what we do when we are looking at the electrolysis of molten compounds, molten electrolytes, which are ionic compounds in the liquid state. They have mobile ions when they are in the liquid state, and we don't have any water present. That's a very critical statement. There is no water present when you're in the molten state. So there will be one cation that will go to the cathode to gain electrons to become atoms again. And more than likely, a solid is going to be formed, and we say the solid is deposited. There will also be one anion that goes to the anode to lose electrons to become an element again. When a liquid or gas is formed at the anode, we say it is liberated. And finally, we must write half equations for each electrode and then combine them to form the full equation. So let me give you another minute or two to copy this information. And then we are going to actually practice one together. All right, guys. So I hope everybody has that information. So let's actually see this in practice now. So we're going back to our supplementary notes now, which is, I'll tell you the page. So page 119 of your supplementary notes. I want you to go there for me, page 119 of your supplementary notes, and we're going to do the first electrolysis question. And we're going to do it together. Make sure you're understanding because you have one after that to do. That one you're going to submit to Canvas. So you have an in-class assessment today. Just remember that for the in-class assessment, all I need you to do is take a photograph and submit it to Canvas. So I want you to watch keenly how I do my example. So the second one you're going to do for yourselves and submit that one. All right. So let's look. So the first example that we have here is molten lead bromide, right? So molten lead bromide would have the formula of PbBr2, and because it is molten, it is in the liquid state, okay? So let's look at the diagram of what happens, and then I'll show you how to fill out the table for the process. So this is my electrolytic cell. You can see my battery set up. I have one electrode attached to the negative terminal. This is actually the opposite, other way. Normally you're accustomed to the negative one being on the right, but it really doesn't matter which direction it is in. Notice just what terminal it is attached to. So we had our negative terminal here, and because it was negative, notice which ions it was attracting. It was attracting the lead ions, all right? Because the lead is positive. So the lead ions, I should tell you, if you have molten lead bromide, the ions that you will have present, literally the compound is going to break apart into its ions. So you're going to have Pb2 plus ions, and you're going to, which are going to be liquid, and you're going to have bromide ions, which are going to be liquid as well. So these were the two ions that we had present in our lead bromide. Lead 2 plus ions, Br minus ions. So lead 2 plus ions are positive. So you can see because they were positive, they were attracted to the negative electrode, which is the cathode. The Br minus ions are negative, so they were attracted to the positive electrode, which was the anode. Now observe what happens when the lead went over. The ions went over to the cathode, they gained electrons. So it said positive ions are attracted to the negative electrode, they gain electrons, and so they become reduced. When the ions became reduced, they formed solid lead. So they went over there as liquid ions, but then they formed solid lead. So you as a scientist would look at the cathode and you'd actually see the lead forming on the cathode. So that is why we'd say you see the solid, because it's a solid, we'd say it's being deposited, all right? Then on the other side now, the bromide ions, which are negative, they are being attracted to the positive electrode. So they're going to the anode, right? And they now are going across there to lose electrons to go back to being bromine again. So bromine element is a liquid or it can be a gas. No, bromine is a red-brown liquid. So you'd literally see at the anode, you would see a red-brown vapor being formed and being given off. So you literally can observe these things happening in electrolysis. So the bromide ion went over to the anode, lost electrons. So it says negative ions are attracted to the positive electrode, they lose electrons and they become oxidized. So this is showing you in a diagrammatic way the electrolysis of molten lead bromide. Now I'm going to show you how do you present that information in a table format, right? So I have done a template of a table for you, and we're going to fill this out together based on what we saw in the diagram and make sure you understand it so you can fill out your own table as well. So we are looking at the electrolysis of molten lead bromide, all right? Now, the first thing I want you to do in your table, you must have 3 columns. You're gonna have one with your cathode, your anode, and then we have some other labels over here. In the first row, I want you to write what were the ions present. So we know lead bromide is going to give us lead 2 plus ions. We're on page 119. It's going to also give us bromide minus ions, all right? Now, which of the ions went to the cathode? The lead went to the cathode because it was the positive ion, the cation goes to the cathode. And the anode, the bromide went to the anode, okay? So that's the first thing you do. I've broken it down to easy steps for you, right? So you fill out the table like this, you're good to go. Next, we have the process. So the next thing you must tell me is what is the process that is done at the cathode? What process happens at the cathode?
Deposition.
Oh, in terms of oxidation or reduction.
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 Yes, very good, guys. And reduction is what? What do you do when you get reduced? Are you gaining or losing electrons?
Gain.
Gain electrons. So I'm making sure I write it there for you to remind you that you are gaining. So at the cathode, we are going to do the process of reduction, which is the gain of electrons. And at the anode, we are going to do the process of oxidation, which is the loss of electrons, all right? So far, we know what process is going to happen. Then the next column of our table will be the half equations. Half equations. So you're going to literally show the process of the reduction with the electrons there. So my lead 2 plus, because it has a 2 plus charge, it needed to gain 2 electrons to go to become a solid atom again. So my lead gained 2 electrons to become a lead solid atom again. And the bromide over here now, there were two of them. So they needed to lose 1 electron each. So there are 2 electrons lost in total. And it forms our bromine for us, which is a diatomic substance. So bromine doesn't ever form one atom by itself. It always forms a pair, which is a liquid. So these are our half equations. Next thing I want you to do in your table is to write the products formed. And the products formed is asking you, what will you visibly observe? What would you see? So in the case of the cathode, we would see the lead being deposited because it's a solid. We say solid lead is deposited. Solid lead is deposited, and what would we describe? How would we describe it for the bromine? You'd say, no, it's not aqueous, it's liquid. Oh, okay. Okay, so we would say liquid bromine is what?
Liberated.
Liberated, good. So I want you to know these terms. So when it says liquid or gas, we say that it is liberated because you would see it. And you could even give more information and say that you know it is red-brown. So red-brown liquid bromine is going to be liberated. So question is said on the diagram, it said that bromine vapor was formed, and you are very accurate in your observation because bromine exists as a liquid at room temperature, But because the electrodes are so hot, they are very hot, the bromine was changed to a vapor. But it was really a liquid, and then it became a vapor because of the fact that it was so hot. So guys, the next thing we need to do is write the full equation now, full equation. And remember, we did this when we were doing redox chemistry, so this is not new to us. So we write the half equation first for the reduction process. And then we write the other half equation beneath it for the oxidation process. And then we will eliminate our electrons once the electrons are equal in number, which in this case they are. Because we had two electrons on the left, we had two electrons on the right. So we are in a good position to eliminate them because they are equal in number and they are on opposite sides of the arrow. So we eliminate these two electrons, we'll eliminate these two electrons, and then we put the two equations together. So everything that was on the left is written back on the left. So now we have the Pb2 plus liquid plus the 2Br minus liquid goes to give Pb solid plus Br2 liquid. And that is our full equation. So that is what I'd like for you to do for me when I ask you to show me the electrolysis of a molten compound. So guys, let me give you a minute to copy that one. And then you are going to be doing one for yourself. And that one is going to be done. And you're going to submit that one to me in Canvas. So you're going to do it at home, write it in. You take a photograph and just go to Canvas and submit that photograph. Or remember, you can just use the Canvas on your phone and use it to take the picture right away in Canvas and submit the picture. All right. So that one is your in-class assessment there. I'm just going to bring it up for you to see that it's already set up in Canvas, ready and waiting for you. So you have your, let me see if I didn't put it right here. So you have your in-class assessment, week number 5, called in-class assessment. If you look in the assignment section, you'll see it, but I'm going to put it in the home section for you as well, so you can see it. All right, so the in-class assessment is what we're going to do now. The classwork is what we do in the last hour of the class. All right. Now, in this, I'm going to ask you to just do the other question that is on page, let me just bring it up for you to see it. So it's the same book question in your book. So in your book on page 120, they asked you to show the electrolysis of molten sodium chloride. So they did give you a diagram to guide you, and I'm asking you to complete this table just as how I completed the other one before that and submit it. All right, submit it for me in Canvas. I'm going to give you 12 minutes to do that. Follow the template that I had. And I want to remind you guys, I must give you a reminder here. Let me just write it on the actual thing. Remember that chlorine is diatomic. So even though sodium chloride has one atom, so this is the formula of sodium chloride, NaCl, right? It has one atom of chlorine in it. However, guys, chlorine cannot exist as just one atom. It has to come off as a pair, and it usually comes off as a green gas. So you have to make sure you form chlorine as a
Come
pair.
off as a pair.
Yes,
Miss, what do you mean by come off as a pair?
because it is diatomic, right? So what I mean, let me just give you a little clue, right? When we get to the part where you're writing the half equations, when you're doing the half equation, right? You're gonna have to show that you must have two chlorides so that you can form a chlorine molecule, because chlorine is not gonna form one atom of chlorine by itself. It has to be a pair, Cl2, because it is a diatomic element. So even though sodium chloride has one chlorine in the formula, you have to use two chlorides, right? So I'm going to help you with the other half equation. So the sodium is going to go to gain one electron, to become sodium solid. And so you're going to have a little challenge here, because the chlorine has to be two of them, because you must form a pair for the chlorine. It's a diatomic element. So this is a situation where you're going to have the electrons being unequal. So when you're ready to combine to make the full equation, you're going to do what I taught you to do in redox, which is that you're going to multiply one equation by 2. Multiply the sodium half equation by 2 so that you can get the electrons to be equal, so you can cancel them out. So this is what you're doing on page 120. You're going to complete the table for the electrolysis of molten sodium chloride using the template I did for the sodium bromide. Giving you 10 minutes to do that, and you submit it in Canvas. And this is just a clue for the half equations. Question? You're going to fill out the one on page 120, just like how I did the example. For persons who don't have the book, remember the assignment is in Canvas, so you can use the Canvas one to just write it off from that, and then you submit it. And I've given you one clue already. I've given you the half equations. I'm going to give you some time now to get that done. 10 minutes should be sufficient time. All right, so we are going to look at what it is I was expecting from you from this in-class assessment. And it was worth 14 marks. And look at how you would have scored the 14 marks, all right? Now, first and foremost, you were to fill up your table. So the first row, you're to tell what ions are present. So I expected you to tell me that at the cathode, you would have had your sodium ion in a liquid state. And at the anode, you would have had your chloride ion in the liquid state, and you'd have gotten 2 marks for that. The next thing I expect you to do is to tell the process. So I expect you to tell me reduction is going to take place at the cathode, which is the gain of electrons, oxidation, loss of electrons at the anode. 2 marks for that. Then comes the half equations. So the half equation at the cathode, you have to show me that the sodium ion gained 1 electron to form sodium solid. 2 marks for that one. And then the chlorine, now, I told you that chlorine, you can't form 1 chlorine atom because it is diatomic. So you must have had 2 chloride ions going to lose 2 electrons to form the chlorine, which would be a gas. So in total for your 2 half equations, 4 marks. Then when it comes to the products formed, I expected you to say is that the solid sodium is deposited, right? And then you would say for the chlorine that it was liberated. Green chlorine gas is liberated, right? So, yes?
Miss, do we have to put green?
Yes, I wanted you to know that, yes, because you're supposed to know the colors of the halogens. So we are doing it for you to score maximum marks, all right? So that's why I want you to give as much detail as possible. Then for the full equation now, it's for 4 marks because you had to show me how you derived the full equation. So you had to show me that for the sodium equation, you had to multiply it by 2 because you wanted to get 2 electrons to cancel the 2 electrons in your chloride. So you would show me that you multiply your sodium half equation by 2, then everything is going to be multiplied, not just the sodium. So you're going to end up getting 2 sodium ions, 2 electrons going to give 2 sodium solids. Then you put the chlorine half equation beneath it with the 2 chlorides going to give 2 electrons and chlorine. Know that the electrons are equal and are on opposite sides of the arrow. We can eliminate them. And so this is our full equation that I expect. 2 sodium ions plus 2 chloride ions go to give 2 sodium solid and a chlorine molecule gaseous. Right? So that was what was expected of you. All right, how did you fare off? If you, well, you will see the, well, I'll put up the mark scheme on Canvas, but I hope you can see what errors you made. That's the importance of this. Go ahead, Gabriel.
Miss, the part where it said green chlorine gas is liberated, is that because chlorine is a gas compared to the liquid bromine is liberated?
At room temperature, remember we did the halogens, you know, and I told you that the chlorine at the top is a yellow gas, chlorine is a green gas, bromine is a red-brown liquid, iodine is a purple-black solid. Those things you have to bear in mind. So because I know that the chlorine was a green gas, that's why it is going to be gaseous. The bromine was a liquid, but because of the heat present in the system, that's why the bromine had turned into a vapor. But if you had written the liquid form for bromine for me, that would not have been a problem either. All right. So that's what was expected of you. So I wanted you to make sure you're comfortable doing the mole 10, because next we're going to do the aqueous, and the aqueous one has an additional thing you have to think about. All right. So guys, I want to give you a breather now, and then I'm going to leave this up for you to write the corrections. Yes.
Miss, do you have to state green chlorine gas is liberated? Because I just wrote it will be liberated. You have to be that specific.
You have to be that specific. So if you didn't put all of that, you won't get the full 1 mark. You get like half a mark. They just said it will be liberated. You get like half a mark for that. So our aim is to train you to get the maximum score. Right? So if you don't put all the information, you won't score all the points. So you learn from now to train yourselves to give specific and maximum information. All right? So I'm going to give you the break, but I'll just leave up this so you can write off the corrections for your break. So guys, we just looked at the electrolysis of molten compounds. However, we have to now bring our attention to what happens when the compound is aqueous, okay? So we have just done that. We're going to be talking about the electrolysis of aqueous electrolytes, and I'm going to give you some notes to guide you as to how you should approach those ones. All right, so I'm going to be going to the whiteboard to do that. So we're going to be talking about the electrolysis of aqueous electrolytes now. So let us go. This, what I can tell you from now, is a little bit more tricky. We have to think about more things now. because unlike when we were looking at the molten, we only had one ion going to each electrode. When there's aqueous, we're going to have two cations going to the cathode and two anions going to the anode. All right, so things get a little bit more tricky, but it's nothing to be scared of. So let us write some notes on the electrolysis of our molten electrolytes. Let's go. Not molten, of aqueous electrolytes. All right, so now, when electrolytes are aqueous, it means that the ionic compound is dissolved in water. Water is a weak electrolyte and thus there will be two sets of ions present. You have the ions from the ionic salt. You also have ions from water. Let me give you an example. For example, I give to you dilute sodium chloride and I put to you that it is in the aqueous state, then you have two sets of ions present. You're going to have the ions that are going to come from the sodium chloride itself. So I want to show you that the sodium chloride would break apart to give its own ion. So you're going to get the sodium ion. You're going to get the chloride ion. But water is there, and water is able to be a weak electrolyte. So water is also going to break apart and give off some hydrogen ions and OH ions. So once I tell you that the substance is aqueous, you're expected to note that water is present and water is also going to contribute its own ions. So that's what I mean when I say that there'll be two sets of ions present when the electrolyte is aqueous. Now this means that there will be two cations migrating to the cathode. However, only one of the two will be selected to be discharged. The same happens at the anode. I'm just gonna use my example that I've been using before in my sodium chloride to illustrate that. That in this situation now, because it is aqueous, you did the molten sodium chloride before, but now it's aqueous, things become a little bit more complicated. Now we have sodium ions that would go to the cathode, and we have hydrogen ions going to the cathode as well. The anode, we're going to have OH ions and we're going to have chloride ions. So now we have 2 ions going to each electrode, but only 1 ion can actually be selected and the other one is going to be left back. We're going to now have to figure out which of the 2 are we going to select. So to determine which ion is to be discharged, we must consider two main factors. Factor number 1 is the position of the ion in the electrochemical series. Factor number 2, if we have a concentrated halide, the other factor is if we had a concentrated halide, then we have to overrule the electrochemical series. So let me go back to what I have here. When when the electrolyte is aqueous, because water is there and water can also give off ions, we will have 2 ions going to the cathode, 1 from the salt, 1 from the water. Same thing for the anode, but only 1 of them can get selected. So now we have to ask ourselves, how do we determine which one is going to be selected? We consider 2 main factors. The first main factor is what is the position of the ion in the electrochemical series, and I'm going to teach you about electrochemical series in a minute. That's the first and the main factor. The second factor to consider is it only is considered if you have a halide which is concentrated. So a halide would be like bromide, iodide, chloride, fluoride. If you had one of these ions and it was concentrated at the anode, then it's going to get preference. It's going to be discharged, and the electrochemical series will be overturned. But the main thing that you're going to look at first is the electrochemical series, and then only look at factor number 2 if you have one of these ions present and it's concentrated. Let me give you another minute because I'm going to go back to the supplemental notes to let you see what is the electrochemical series and how we can read it to determine which ion is going to be discharged in preference. Right. 20 more seconds and we're going across to the supplementary notes. All right, so we're on page 121 of your notes, and this is just to remind you, it's just kind of what we said a while ago, that there are certain factors which affect what products you get in electrolysis. And it says here that there are 3 factors. A while ago, I told you about 2 main factors, but there are 3. But I won't introduce you to the 3rd one just yet. But the 3 factors that we said that would affect what ions you get released would be: first, the position of the ion in the electrochemical series. The second factor is the concentration of the ion in solution. And remember, I just said to you that that factor number 2 is only relevant if you have concentrated halides. It's not relevant if you don't have a concentrated halide. The 3rd factor.
This they gave us before, those are the only ones.
So these were the same 2 that I had on the whiteboard. The first 2. But then there's a 3rd one that you're being introduced to now. Was that what you were asking?
No, Miss, the concentrated halides that you gave us, are those the only ones?
Yes, so remember halide, yes. So the halides are the ones in the halogens. So the 4 that I gave you, those are the 4 ones that you need to remember.
Okay, Miss.
So the other one, the other factor now, which is factor number 3, which is not, I'm not bringing in that yet, but you just have to know it. The nature of the electrode can also be a factor, and that is if the electrode is inert versus being active. All right, so just make a note of that for now, but we are not going to really get into factor number 3 for today, but we are definitely going to be doing factor number 1 and number 2. So now we're going to talk about the position of the ion in the electrochemical series, because that's the main thing that you need to know when you are dealing with aqueous compound. What is the position in the electrochemical series?
Miss, can you go back up for a second, please? Thank you, Miss.
Now, this is the series. This charge in preference.
Miss, you're
I
muffled.
can't hear you properly.
Miss, Miss, we're not hearing you properly. No, Miss, you're not clear.
All right, just checking if there has been any improvement. All right, so I was saying to you that the substances, the ions, when you look at the list of the ions, the ones that
Miss,
are,
now you're extremely low.
oh, all right, just give me a moment there. Let me see what I can do to solve that. Okay, so I'm trying again. Is it any better? Let me just see. Any improvement?
Yes, Miss.
You hearing me better now? All right, so
Yes.
I was saying that we had a list of ions, right? And that for each list of ions, each of the list of ions, essentially, we look at.
Miss, I still can't hear you.
Oh, you still can't hear me. All right.
Yes, Miss, you're very low.
Okay. Another thing here. All right, guys. Definitely, I hope you should be hearing me better now. Is it good?
Yes, Miss.
Yes, that's better.
All right, great. All right, so I was saying to you that the electrochemical series has ions. So let's look at the series here. But the key thing I wanted you to note is that there is a list of ions for the positive ions, and there's a list for the negative ions. And when you're looking at the list, anyone that is to the bottom is going to go off in preference to anyone that is above it. All right? So like for here, we have a list, right? So we have like You're seeing sodium, potassium, so potassium and sodium, calcium, magnesium, aluminum, zinc, iron, tin, lead, hydrogen, copper, and silver. But this is how I want you to remember this series, right? I want you to remember where hydrogen is in the series. And I want you to see that hydrogen is to the very bottom of the series, all right? Now, means that hydrogen, more than likely, if hydrogen is going to be there with any one of these ions, whether potassium, sodium, because hydrogen is lower down in the series, hydrogen is going to be discharged, all right? So the ions that are lower go off in preference, all right? So just for example, if you had a competition between, like in this situation, if we had a competition between sodium and hydrogen, right? You can see that hydrogen is lower down, right? So in the series, hydrogen is down at the bottom versus sodium, which is way up to the top, right? So it means that hydrogen is going to get to go off in preference to the sodium, right? So hydrogen is selected, right? Now let me give you another one and you tell me what you think. What if I gave you hydrogen ions and I gave you copper ions, right? Which one do you think would get selected at the cathode?
Copper.
Copper, right? Because copper is lower than hydrogen in the series. So I want you to remember that the only thing I really want you to take away from this is that most times hydrogen gets selected. Only if there is copper or silver can they outcompete the hydrogen. That's the main takeaway message from this. I don't want you to try to remember the series, but just remember that hydrogen is to the bottom. And so most times hydrogen gets selected. So you can add these annotations. The most times hydrogen gets selected, except for when copper or silver is present. So that is what I want you to remember. I don't want you to swat the series. Just remember the principle, because hydrogen is so low, only 2 ions are really below it that can outcompete it. And remember that the hydrogen ions are coming from the water molecule. So most times the hydrogen from the water is the one that gets chosen and not the other ion that is there. So remember that most time hydrogen gets selected except for when copper or silver is present, right? So let's look over to the other side. This is the series for the negative ion, guys. Now looking at the series, you see that the OH is to the bottom of the series, right? So most of the times, if you have OH competing with anything else, the OH is going to win because it's at the bottom. So I want you to remember that for the second series here, most times the OH gets selected. There's only one time though when OH doesn't get selected. And this is when you have a concentrated halide. The halides are the negative ions of the group 7 elements. So if you had a competition, and I'm going to give you an example. So if I had a competition against hydroxide and dilute chloride, hydroxide is going to win. However, if I put up the OH against concentrated chloride, the chloride is going to win. Because the concentrated halide can overrule what the electrochemical series says. And I'll give you another one. If I had OH competing against sulfate, OH is going to win. So I'm just illustrating it to you that most of the times the OH is going to be winning. Most of the time the hydrogen wins, but remember copper can win against the hydrogen. And in the case of the OH, it wins most of the time, except for when a concentrated halide is present. I'll give you a minute or two to copy that. And then we're going to put it into practice by actually doing electrolysis of some substances. All right. So let me give you 2 minutes. All right, one more minute for you to get that down. All right, so remember, main takeaway point, guys. If you have an aqueous electrolyte, you have to think that water is there. Water supplies 2 ions. Water gives H plus ions. Water gives OH ions. Then you're gonna have competition at the cathode, or you're gonna know who is gonna win. You look at the electrochemical series. Anybody that's furthest to the bottom will get preference. Hydrogen is way down to the bottom, so most of the time hydrogen is the one that gets to get discharged and the other one has to stay behind. Over the negative ion category, OH is at the bottom. Most of the time the OH gets discharged and the rest of them stay behind. But there is a one time when OH is not does not get discharged, and it's if we have a concentrated halide, which can be a concentrated chloride, concentrated bromide, concentrated iodide, concentrated fluoride. But if the halide is dilute, it can't overrule the OH. The OH is going to win. It can only overrule it when it's concentrated. All right. That is the take home point that I want you to get. All right. So we'll look at these other notes some more, but I want us to actually put in practice. We're going to actually do the electrolysis now of an aqueous electrolyte using an inert electrode. Before I do that though, there's something else I want you to know now. Before we do these practice questions, just want you to make a note that when we were doing the electrolysis of molten, you didn't need to write a conclusion, but when you're doing aqueous, you need to write a statement. After you've done the full equation, you need to write a conclusion. All right, so when doing electrolysis of aqueous electrolytes, you must write a conclusion after the full equation. You must write a conclusion after the full equation. So that is something that you have to remember. So when you were doing the molten one earlier, when you had reached the full equation, you stopped. But there's another additional step now that you have to do with an aqueous electrolyte. And these are the things I want to see in the conclusion. So the conclusion must include 1, products formed at the electrodes. Number 2, the ions left back in solution. 3, check if a new substance was made. 4, check for changes in color. Sometimes the solution will change color. 5, changes in pH. The final thing you check for in your conclusion is that you check for changes in concentration. So it gets a little more, as I said, there's an additional thing you must do when you are doing aqueous, and that's the conclusion. And this, if you do this checklist, you will always be able to write a conclusion for your electrolysis after you're finished. Because what you're doing is you're checking to see, you're just going to tell me, okay, what came off at the anode, what came off at the cathode. Then you say, if we took out 2 ions, which 2 were left behind in the solution? Because 2 are going to come off, 2 are going to be left behind. You're going to check to see if the 2 that are left behind can react to form a new substance. So sometimes the ones that are left behind can actually give you something new. So the ones in solution, can they react to give you something new? Will there be any change in the color of the electrolyte? Will there be any changes in the pH? Will there be any changes in the concentration of the electrolyte? And I'm going to tell you when you might see changes in the concentration. So sometimes if the water ions are being removed alone, then the electrolyte will get more concentrated than what it was at the beginning. So this is your checklist for writing your conclusion after you have written your full equation. So I must tell you that it's not all the time that you're going to have all these changes, you know. Sometimes you're not going to have a new substance being made. Sometimes it's the same old substance that's there. So it's not all the time you're going to have a change in color. It's not all the time you're going to have a change in pH. But my aim is to show you what to check for so you don't miss anything. And it's not all the time you will have a change in concentration, but check for all of them so that you know that you're writing a full conclusion statement for me. All right, I'm going to give you a minute now, and now all of what we have learned, we're going to implement it and do at least 2 of the electrolysis of aqueous compounds, and the rest of them, that will be for your classwork. Yeah, so I'm going to make sure I do 2 of them with you, walk you through the process, and then the others will be for your classwork. So make sure you are very alert and attentive when I'm doing the examples so that you can manage to do the others on your own. I'll give you another minute to finish copying this. All right, was everybody able to write off the conclusion or the conclusion must contain? Yes? Everybody's had that? All right, I'm going to go back to the supplementary notes now. And we're going to get through our 2 equations together now. 2 examples, all right? So 2 examples that first one we're going to do is dilute sulfuric acid. I'm going to go through the diagram and then we are going to fill out the table. So this is the formula of sulfuric acid. This is H2SO4 and it is in the aqueous state. So when you do the electrolysis of sulfuric acid, we can look at it and we see that hydrogen gas is being formed at the cathode. Over the anode, we see oxygen gas being formed. In sulfuric acid, we need to explain how did we get oxygen gas? How did we get the hydrogen gas? That's the diagram. Let's fill up the table. Everybody, let's fill up the table together. So we are going to fill up the table now. We are looking at the electrolysis. So it's electrolysis of aqueous H2SO4. All right. So the first thing you do in your table, just like we did when we're looking at the molten one, we look for the ions present. Now there are 2 sets of ions present in this. So the sulfuric acid is going to break up to give us hydrogen ions and sulfate ions. But water is also there because it is aqueous. So water also gives us H+ ions and OH ions. So guys, over at the cathode, we're going to have 2 sets of hydrogen ions. So 1 hydrogen ion that came from the sulfuric acid and 1 coming from the water. So either way you take it, we have 2 sets of hydrogen ions going to the cathode. What are we going to have going to the anode?
Miss, could you repeat that?
Okay, so I'm saying that if you look at the sulfuric acid, right? When the sulfuric acid is in water, it's going to split apart to give us H+ ions and sulfate ions. But remember that because it is aqueous, it means water is present and water also will split apart and give us ions. So it will give us H+ ions as well and OH ions. So what I was saying was that we're going to end up getting H+ ions from 2 different sources going to the cathode. So H+ ions coming from the sulfuric acid, let me draw it in a different color. And we get some other H+ ions coming from the water. But you get basically H+ alone from 2 different sources going to the cathode. Understand that now? All right, so guys, what will we have at the anode? Which 2 ions are going to go to the anode?
The sulfuric acid and the sulfate and the hydroxide.
Sulfate and the hydroxide. All right, so then you're going to say the next part is going to be ion selected with reason. So you're going to tell me which one is going to be selected. Well, clearly, hydrogen ion is going to be selected because it's the only one there. I don't have to give a reason for that. So the ion that will be selected over by the cathode will be the H+ because literally it was only that it was only one choice. But can you tell me which one is going to be selected by the anode, please? Which one would be selected? If I have competition between sulfate and hydroxide, guys, which one is going to win? Hydroxide. Very good. All right. You say it's lower in the series. That's the reason. Very good.
Miss. Oh, never mind. Miss. Never mind.
Okay. So basically, we're doing it just like how we did the molten, you know. We start off with the ions present. Which one are we going to select? What process are we going to do? Reduction happens at the cathode, oxidation at the anode, and then now we're going to put in our half equations. So My hydrogen is going to be selected, and this is it now, guys. Hydrogen is diatomic, so you always have to form a hydrogen molecule. So I have to make sure I form a hydrogen molecule. I can't form one hydrogen atom by itself. So notice I must have two hydrogen ions gaining two electrons to form me a hydrogen molecule. And then guys, for the OH, I want you to swap this equation. OH, whenever OH goes to the anode, there are always four of them that goes there. They will give off 4 electrons, form 2 water molecules, and 1 oxygen gas molecule. So the equation for OH, you have to just memorize it. 4 OH goes over to the anode to give off 4 electrons. We get 2 water molecules, 1 oxygen molecule. Question? Why the 4? So I'm saying that this is a standard equation you have to memorize, because for you to create the 2 water molecules and the oxygen, you need to lose 4 electrons. So each OH has an extra electron. So if you have 4 of them losing 1, that's how you get 4 electrons being lost. But it's something you memorize. You don't create the equation. You must just memorize that this is the equation for the hydroxide. When we come to the products, remember products will be what you will see. What can you physically see? So you would see the hydrogen gas. You'd see bubbles of hydrogen gas at the cathode, and it is being liberated. It's being liberated. So over by the anode, guys, even though water is being formed, you're not going to see the water being formed. All you're going to really physically see is that you're going to have oxygen gas liberated. Follow me, all right? Make sure you're writing it along. Here comes the full equation time now. Because I have 4 electrons at my anode, I need 4 electrons also for the hydrogen to be able to cancel it. So I'm going to have to multiply the hydrogen equation by 2. So I could get 4 electrons in it as well. So that's going to end up giving me 4H plus 4 electrons, going to give me 2 hydrogen gas molecules, all right? So we have to multiply the hydrogen equation by 2 in order for it to add up. And then I write back the OH equation. Guys, I'll be writing this off, you know, because you need to be able to do the other ones when you get your time to do it, all right? So guys, so the full equation now, I'm going to be able to eliminate my electrons now because the electrons are equal. So my full equation is going to be 4H plus 4OH, going to give me 2 hydrogen gas plus 2 water molecules plus oxygen gas. That's what I get when I combine the 2 equations together. So that's the full equation there. Just remember that you have to make sure that the electrons are equal in number. So I noticed that my hydrogen equation had 2 electrons, so it would not have been equal in number, and that's why I had to multiply it by 2 to get the electrons to be equal. Are we following up to this point? Right. Remember, you have your own ones to do, you know, so make sure you get it from now. So remember what I told you had to do after you did your full equation? After you do a full equation, when you're doing an aqueous electrolyte, what is the other thing you have to do?
Write a conclusion.
The
You have
conclusion.
to write a conclusion, yes. Remember this guidelines I gave you for the conclusion? All right, we're gonna use the guidelines right now and we're gonna write ourselves a nice conclusion for this. What's the first thing we should write for in the conclusion? Products formed. So we're gonna say hydrogen gas liberated at cathode. So the first thing I'm doing is the product. So hydrogen gas liberated at cathode and oxygen gas liberated at anode. Okay. And what should be my second thing I check for in my conclusion? Okay, ions left behind. So if I took out, remember I took out my OH ions and I took out some of the hydrogen ions, guys. So what do I have left behind? I still have some hydrogen ions left behind and I have some sulfate ions left behind. Now, if I have hydrogen and sulfate behind, you know what they're gonna do? They're gonna react with each other and they're gonna form sulfuric acid. But guys, is this a new substance? Is sulfuric acid new? Because remember in the conclusion, I said, look, if the ions left behind can make something new. I'm saying the two ions left behind were the hydrogen and the sulfate, but when they come back together, is it something new? Or was that what we had originally there?
It was originally there.
It was originally there, so it's not new, right? So we started off with sulfuric acid, we get back sulfuric acid. It's not new, it's still the same old sulfuric acid, but all right. So it wasn't anything new. So what else am I to look for, guys? So no new substance form. So not new. It's not new. It's the same thing that was there before. What else should we check for? Yeah,
Change
so
in
no,
color.
yeah, there'll be no color or pH changes because sulfuric acid is transparent. So this has no color or pH changes. All right. What else am I to check for? There were no pH changes either. But I never added any H plus or I never changed the pH. So what is my other thing to look for now? Check for changes in concentration. And then I gave you a clue, right? If you notice that the water is the one that is being removed, then what is left behind must become more concentrated, right? So we notice that we're losing H plus and OH ions removed. The H plus and OH ions were removed, right? And that means that that's water because H plus and OH comes from water. So water was being removed, therefore, the sulfuric acid became more concentrated. All right, we're almost there, guys. We're almost there. Then you can take a breather and then you can attack your classwork after. So in this situation, because I was taking out H plus and OH ions, that basically is like I was removing water. So if I have a solution of sulfuric acid and I'm taking out the water out of it, then the solution that is left behind is going to become more concentrated. So it became more concentrated. So make sure you have this information because you remember you have a classwork, which is similar. Get down information. I'll give you one more minute and then we're going to do one more example. And what I can do, I can put this, I'll put it up in Canvas for you, the examples, so that you can, instead of having to write it off, put it in Canvas, all right? So I'm just gonna go ahead because I'm gonna put it in Canvas for you, but are you understanding what is happening so far? All right, so I'll put this in Canvas for you, no worry. Let us see if we can get through one more together. This time now, we're gonna do concentrated sodium chloride. All right, I'm gonna skip the diagram. I'm gonna go straight down to the table. You don't have to copy this one because I'll put it in Canvas for you. So concentrated sodium chloride is called brine. So if you ever see it and you see somebody telling you about brine, you know they're talking about concentrated sodium chloride, okay? So guys, I want you to tell me now, your time to talk. What ions am I going to have at the cathode for this concentrated aqueous sodium chloride? So definitely sodium ions are going to come over here, but there's another ion that's going to come there as well. Remember, this is aqueous. Come again?
Hydrogen.
Hydrogen. Remember, once it is aqueous, water is there. So hydrogen is going to be coming out, is going to go there. So I am not going to always write it out for you and make you know that water is there. I expect you to remember that. So what is going to go to the anode now? So the chloride, remember once it has a negative charge, it's called chloride. And what other ion is going to go there? What other ion is going to go there? The
Hydroxide.
OH. Very good, because remember there is water present. All right, so here, this is it now. So please notice that the chloride is concentrated now. All right, so let us see if you can tell me now which ion is going to be selected at my cathode. So I have a competition between sodium and hydrogen. Who is going to win?
Hydrogen.
Hydrogen is going to win because it's lower in a series. Remember who I told you can win the hydrogen? Do you remember which one can win against hydrogen?
Is
Which
it
one can
copper?
win? Copper
silver.
or silver. So if
Silver.
it's not copper or silver, you know hydrogen is going to win, right? All right, guys, over here now at my anode, this is a little tricky because my halide is, chloride is a halide and it is concentrated, competing against the OH. Which one do you think is going to win? Concentrated chloride competing against the OH. Which one do you think is going to win? The concentrated chloride, guys, is going to win because it's a concentrated halide. That can overturn. Normally, if it was dilute, the OH would have been the one selected, but not when it's concentrated. So processes will be reduction, oxidation, and then half equations now. Half equation times, so my two hydrogens, gonna gain 2 electrons to become hydrogen gas. And then I'm gonna have to use 2 chlorides as well because chloride is diatomic to form my chlorine gas. So now it's time for my products. I am going to see hydrogen gas. So this one, I'm going to see hydrogen gas. Almost finished, guys. Hydrogen gas liberated. And then over here, I'm going to see green chlorine gas liberated. All right. Next, it's time for my full equation. So luckily, the electrons are equal, so I don't have to multiply anything, right? So I just have to eliminate my electrons. That leaves me with 2H plus 2Cl minus, going to give me hydrogen gas and chlorine gas. All right, here comes my conclusion now. So in my conclusion, I know that hydrogen and chlorine gas were liberated. Those are my products. All right, tell me the next part of my conclusion. What else should I write in my conclusion, guys? Ions left behind. So what were the ions left behind? All right, so left behind, I had the sodium that never came off. And what else was left behind? Hydroxide. So can sodium and hydroxide react together? Yes. So a new substance in this case is going to be formed, which is going to be sodium hydroxide. Yes, so sodium hydroxide is formed, which is a base, so it's going to increase the pH. So the pH increases because this is a base, all right? There were no color changes, no color changes. So that is what I would do for my concentrated sodium chloride. But when you get your homework now to do the dilute sodium chloride, you're gonna see that it's gonna be a bit different because the halide is not gonna be concentrated anymore. So these are the ones you're gonna do for your classwork. I'm gonna put this in Canvas, this one that I did for you. And then for your classwork, you're gonna do this one for me, electrolysis of the dilute sodium chloride. You're also going to do for me electrolysis of copper sulfate, and I'm going to give you a clue with the copper sulfate that the blue, if the blue color is going to fade. So this is what we're gonna have, blue color is gonna fade. So when you get to the conclusion part, you'll see that if you're gonna remove copper, the blue color of the solution is gonna fade because copper sulfate is blue. And also you're gonna form sulfuric acid. And that means that there will be a decrease in the pH. I'm just helping you with the conclusion for this one. So you're gonna have to do this for classwork as well. So yeah, and molten calcium bromide. So you're gonna have like 4 of them to do for your classwork. You're gonna do molten calcium bromide, and remember, when it's molten, there is no water present, so there is no competition between anything when it's molten. If it is aqueous, there's competition. If it's not aqueous, there is no competition, right? So that's what you're gonna do for me for your classwork. You're gonna do some of the rest that are in the supplementary book, right? I have selected the ones that I know you can manage. And I want you to just apply the principles, give me some beautiful tables, lovely conclusions, and you should be good to go. What I'm gonna do here, the assignment is already set up in Canvas, but I'm gonna just put these pages here with these examples that you can use them for reference when you're doing your own work in Canvas. All right, and we're gonna stop right at this point here. And the assignment, I've left it open until late tonight so that nobody has an excuse as to why you could not submit it. All right, but ideally, guys, do it right in the class time. All right, so this is where we're gonna stop. I just want to know, do you have any questions? I'm gonna be putting these pages in Canvas for you. Any questions? Remember, I'm putting it in Canvas. I'm just gonna put it in Canvas in the next minute. All right, so if you have no questions, all the best with the classwork. Do your best, and you can look back at your in-class assessment at your scores and the comments you got for that. All right? If you have any concerns, you can send me a message on WhatsApp. All right, so we're gonna stop here. And so I put in this document here for you. All the best with your work.